Hello everyone and welcome to the Game Engine programming series where we write a game engine from scratch. Previously, we started setting up the building blocks for a forward plus render path, and so far we created the geometry path submodule that will be in charge of rendering the geometry using the lighting information. Today we are going to add a new submodule that will be used for post-processing the image that's produced by the geometry path. Let's do a quick recap of what we did in the previous episode, which was about geometry paths. Here we added a submodule as a placeholder for what will be the geometry path, where we do a depth prepass and a render pass using forward plus rendering. We wrote a function that creates the main buffer, which is an intermediate render target, and the depth buffer, which gets written to during depth prepass. We also wrote a function for creating a root signature and a pipeline state object so that we can test our render path. Of course, later on we'll have per material root signatures and PSOs depending on which objects are being rendered. However, for now we just render a full screen triangle and fill it with a constant color. We also release everything when shutting down. This submodule is initialized in core CPP so that we can call its functions during rendering. We also added a helper class for batching barriers and applying them together. You can find this class in helper's header file. In the render function, we transition the buffers for each step, set render targets, and run depth prepass followed by the geometry and lighting pass. Right now, the render pass function is empty and gpass's render function simply fills the screen with a constant color. It also passes the frame number to the GPU using a root constant parameter. Of course, we still need to fully implement both our vertex and pixel shaders, but they are already valid and can be used. That's in a nutshell what we did previously, and now we can continue setting up the post-processing submodule. Similar to gpass, we start by adding a header file for post-process. I'll use the effects namespace since it's about post-process effects. We add initialize and shutdown functions as usual and proceed to add a CPP file for their implementation. Right now we don't need any buffers for post-processing because all it does is to copy gpass's main buffer to the swap chain's back buffer. To do this, we need to load shaders to the pipeline and pass some data to these shaders. Therefore, we do need to create a root signature and a pipeline state object. It's rather similar to how we did it for the gpass, so let's just copy that code and rename the variables. We also need to include the shaders header file for using engine shaders. Because post-process uses opaque geometry and doesn't use a depth buffer, we can remove depth state and blend state from our pipeline state subobject stream. Also, we are going to render to swap chains back buffer, so we need to use the back buffers format for the render target format. Finally, we need to create a new pixel shader that samples pixels from GPass main buffer and outputs them to swap chains back buffer. Again, I'm going to write this shader properly later when we write the other shaders. You don't have to wait long though, because that's gonna happen in this video. Great, we are still up and running, so let's continue. I would like to move the test windows more towards the center of the screen first, so we can see them properly. The postprocess shutdown function releases the root signature and PSO. Now we are ready to add our shiny new post-processing submodule in the renderer by initializing and shutting it down in core CPP. As you can see, the FX root signature and PSO are created successfully. Next, we need to add a new function in order to do the actual post-processing. I wonder how many of you correctly guessed what the name of this function was going to be. It takes a command list, and for now I'm just going to pass a render target view that will be used for the final post-processed image. Again, very similar to GPass render function, we need to set the root signature and the PSO first. Then we set the primitive topology to triangle list, since we are going to render a full screen triangle. We'll use the provided render target view to set the render target using omSetRenderTargets function and issue a draw call that generates 3 vertices. Because we need to read from GPass main buffer, we have to pass the descriptor heap that contains main buffer's SRV, along with the index of that SRV within the heap. So we need to create a descriptor table root parameter, and since we are using bindless technique, we have to define an unbounded range of shader resource descriptors. Using range offset append for descriptor count and setting descriptor volatile flag lets the API know that we would like the range to be unbounded. So the first root parameter is a 32-bit root constant that will hold the index of main buffer's SRV within the heap, and the second root parameter is the GPU address of the SRV descriptor heap. In post-process function, we can set the corresponding values, but first we need to access the GPass buffers. So let's add a couple of accessor functions. Remember that although we have an index in descriptor handle structure, it's only accessible in debug build. We could calculate the index from heap start address, descriptor's handle, and the size of descriptors. However, it's easier to just remember the index, so let's make it available in all build configurations. Unfortunately, this will also increase the size of our descriptor handles. But we can always consider other ways of calculating this information if it turns out to be too inefficient. Looking back at the root signature, notice how defining root parameters and setting those parameters happens in two different places. Right now we only have two root parameters, but it will become increasingly hard to remember what parameter index belongs to what parameter when we have more root parameters to deal with. To make this easier and less prone to errors, we can define an enumeration which contains an item for each root parameter. Then instead of using numbers, we can use the name of each root parameter that we would like to set. For the current implementation of post-process submodule, we have root constants and descriptor table as the root parameters. When using the enumeration, it's easier to give it a shorter name by using type aliasing. Now we don't have to remember root parameter indices anymore. This is all we need for the post-process function for now. Let's call it in the render function. I need to use the correct name for GPass main buffer and depth buffer. Trying to run the application right now results in an error caught by the debug layer, which tells us that we are using a descriptor table as a root parameter, but we haven't attached the descriptor heap to the pipeline yet. And of course that's entirely true, so let's set a resource descriptor heap. Before setting the descriptor heap, though, let's make all accessor functions with the return value non-discardable, which means that we would get a compile time warning if we call them without using their return value. I'm doing this to prevent some bugs like the one that we had in the last video, where I accidentally called resource function instead of release. Making the same mistake now would give us this warning. Going back to setting our descriptor heap, we could do this in any or all of the submodules, but since we are using a single descriptor heap for bindless resources, we can simply set it once at the start of the render function. Remember that at any time, we can only attach one resource descriptor heap and one sampler descriptor heap to the pipeline. So if you need to change the heaps, you need to set them again where they are needed. Before moving on, I would like to have the option to restart the application without having to manually close and restart the application's executable. That's because we are going to write engine shaders in a minute, and to apply the changes we make to those shaders, we need to recompile them And of course, that happens when we initialize the application. We could also go through the trouble of setting a sentinel that frequently checks for engine shader source file updates, stops the rendering, recompiles the shaders, and reconstructs the PSOs. But that would add a lot of extra code in the engine that we won't need eventually. So what I'd like to do is to soft restart the application by calling shutdown and initialize functions when I press F11 on the keyboard. Because this will close all windows, we need an extra boolean variable so that postQuitMessage function won't be called if we are restarting the application. Then we move the code from the member functions to the free functions to be able to call them in the Windows message handler. Now every time I press F11, the application is shut down and reinitialized without actually quitting. Of course, we need to reset is restarting to false if we want to ever really quit the application. So let's reset that to false when the application is initialized. Great. Now we can proceed and write our engine shaders in a way that actually does something interesting. Let's start with the full screen triangle. When rendering a frame, we often need to copy pixels from one render target to another. For example, if we wanted to apply some post-process effects such as bloom, we would need to blur the GPath main buffer and write the results to a new render target. To do this, we need some minimal geometry that covers the entire screen. One common method of doing this is by rendering a quad which consists of two triangles. Although this is widely used, it's a bit inconvenient to set up since we need a vertex buffer for the quad's vertices. In addition, because rasterization happens in groups of pixels, typically 4x4 pixels, this means the groups that overlap the border between the two triangles get rasterized twice, which is a wasted effort. DirectX 10 and later make it possible to fix both issues by drawing a single full-screen triangle. However, before getting to that part, I need to talk about normalized device coordinates. Object positions in a 3D scene are given in world coordinates. So any position from minus to plus infinity is possible. When viewed by the camera, only the part of the world within the camera's frustum is visible. We get the position of objects with respect to the camera frustum by doing view and perspective projections. I'll talk about these transformations in another video when we actually render 3D objects. But for now, the blue capped pyramid shape here is the result of doing these transformations. The objects outside of this frustum are clipped and not rendered in the scene. This is called the clip space. Finally, all points in the frustum are transformed in such a way that will fit within a block with normalized coordinates. I think the name is a bit misleading though, because the width and height of this block are 2 units wide. So everything that's visible to the camera is transformed into this volume. The ranges of x and y directions go from -1 to 1. In DirectX's normalized device coordinates, z goes from 0 to 1. Also note that the origin is at the center of the front face. Looking at xy plane, we can render a triangle with vertices that reach outside of the NDC volume. This way, the front face of NDC is completely covered by the triangle, whereas the region outside of it is clipped during clip space transformation. We can also assign texture coordinates to this triangle. As you can see, within the NDC, UV ranges are normalized as well. This is all there is to it, but if you'd like to know more about the graphics pipeline from the hardware's perspective, I'd recommend reading this excellent series of articles by Fabian Giesen. Now let's go and write the vertex shader. To implement this shader, we can use the vertex IDs and generate the texture and position values. This can be done simply by using an if-else statement where we hardcode the values depending on the IDs. In the following video, I'll write this shader without using conditional branching. That's it for our vertex shader. Let's continue with post-process pixel shader. As I mentioned before, this shader just copies every pixel from GPass main buffer to the swapchain's back buffer. Remember, we passed the main buffer's SRV index using a root constant parameter. It will be mapped to a constant buffer structure in our shader like this. Note the B1 register. That's where our 32-bit root constants are mapped to. The second root parameter was the descriptor table, which is an unbounded range in our resource descriptor heap. Texture resources are mapped to a T register. In this case, we can access all texture 2D views within the heap by mapping an array of textures to T0 register. Optionally, we can also use register spaces. This would be useful if we wanted to bind the descriptor table multiple times to access different types of textures. For example, if we had a texture cube in there, we would need to bind another descriptor table as an array of texture cubes, and this time we could map it to the same register but use a different register space. Shader Model 6.6 introduces dynamic resources, which eliminates the need to use descriptor tables in root parameters. We could simply use a keyword for resource descriptor heap and sampler descriptor heap and directly index into those. At the moment of this recording, Shader Model 6.6 is not released with Windows SDK, and I would need to install DirectX 12 Agility SDK in order to use it. Later, when it's included in the Windows SDK, I might rewrite our shaders to use dynamic resources, as it makes it a lot easier to access resources. As I already mentioned, this shader samples each pixel in the main buffer and outputs it to the render target, which is the swapchain's back buffer. I forgot to actually return the color value, so let's fix that error. Success! Remember that GPass's main buffer was filled with this lovely magenta that we see here. This means that we managed to set up our render path successfully, and now all we have to do is to render wonderful images. Speaking of which, why not do that right now? To do something that is slightly more exciting than our pink solid fill, I need to pass the dimensions of the render surface and the frame number. I was watching a video by 3blue1brown the other day, which was about fractals, and I thought why not render a fractal using our game engine. By the way, 3blue1brown is one of my heroes, and if you're not already familiar with his channel, I would strongly recommend it. Just go and watch one of his videos and you'll see what I mean. Anyway, before writing the function, I'm going to normalize the dimensions of this view by dividing the pixel positions by the width and height of the render surface. Of course, we can use the provided UV parameter for this as well, but as we'll see in the next video, I'm going to jitter the pixel positions a little bit to do some kind of poor man's anti-aliasing. Doesn't matter, we are just having fun at this point. Because this is just for fun, I'll put the fractal code in an include file instead of putting it directly in this shader source file. Let's create a file that I call fractals.hlsli, where I stands for include, and include it in our post-process pixel shader. When running the application, shader compilation fails because the compiler doesn't know where to find this include file. Before addressing this issue, I'd prefer not to crash the application when something fails to initialize. Therefore, we can check if the render platform contains a valid enumeration in the shutdown function. Now it doesn't crash anymore. Let's continue with our shaders. To help the compiler find our file, we need to give it the path where it is located, which is of course the same path as the shader source files. So we can add a new parameter to the list of compiler options that contains the path to include files. And once again, everything is fine and dandy, and we can finally write the fractals shader code. Since I'm going to write a fractal function, let me explain a little bit about complex numbers and the Mandelbrot fractal. Here is an axis that represents the real numbers that we all know and love. R is a set that contains all integers, natural, fractional, and rational numbers. As you can see, it also includes the square root of any positive number. However, it does not include the square root of negative numbers. Because taking the square root of a negative number didn't make much sense conceptually, but was needed mathematically, the term imaginary was used to refer to these numbers. To expand the set of real numbers, a new axis for imaginary numbers was added. All real numbers are now a subset of the complex set of numbers, which consists of real and imaginary parts. Letter I can be thought of as the scale of the imaginary axis, which is equal to the square root of -1. Two complex numbers can be added in the same way real numbers are added. We add real parts and imaginary parts separately. We can think of a complex number as a two-dimensional vector. Then addition is a component-wise vector addition. Multiplication is also exactly the same, except that whenever we multiply I by itself, we get I squared, which equals -1. And the square of a complex number can be written as follows. That's it. Now you are an expert in complex number addition and multiplication. Let's see how we can use this rather uncommon skill to draw a Mandelbrot fractal. Before using complex numbers, let's have a look at this function that's simply the square of x plus a constant. We can create a series of functions in which we feed the result of the previous function into the new one. For example, if we choose x to be 0, then we get c for the first function, then c squared plus c for the second one, and so on. Choosing 0.5 for the value of c, we get 0.5, 0.75, 1.0625, and so on. As you can see, it's a rather simple exercise. Now let's generalize this function by using complex numbers. It looks pretty much the same, except z and c are now complex numbers. To evaluate the function series, we need to use complex addition and multiplication, which we just talked about. Plotting the result of each function on the complex plane, we see that for some values of c, the series will diverge to infinity, whereas for some other values, the series will either get trapped between a couple of values or converge to a finite value. If we color all divergent values white and converging or trapped values black, then we get the famous Mandelbrot fractal. Note that when we get to a point whose distance to origin is larger than 2, then we know for a fact that that point is divergent. We can also count the number of steps it took to get to a point of divergence, and depending on that number, assign a color to the starting point C. That's how we get the colorful Mandelbrot fractal. If you are interested in an infinitely more pleasing explanation, please go ahead and watch this video from 3 Blue 1 Brown. I'll put the link in the video description. Now we are ready to write the Mandelbrot fractal code. First, we need to put the fractal near the center of the window. To do this, I'm going to define the bounds of the fractal and use the UV coordinates to scale and translate it to the right place. This is the C constant in the fractals formula. Next, we re-evaluate this formula for as long as the length of z is less than 2, or the number of iterations reached the maximum that we defined in the max iterations constant. As I pointed out in my explanation, multiplying complex numbers is a bit different because of the imaginary I value, so we need to define a function for computing the square of a complex number. Instead of calculating the length of z, it's faster to use the dot product, which effectively gives us the length squared of z. And because we'll stop iterating at lengths larger than 2, we stop at square length of 4. When this happens, we'll give this pixel a color that depends on the number of iterations that we did. So let's write a function that calculates this color. Here you could use any color mapping that your heart desires. I'm going to use a bluish palette for our fractal. Obviously, we need to call draw Mandelbrot function to get anything displayed. No fractal, although we did get a blue-gray background. This is because in all my excitement, I forgot to pass the window dimensions to the pixel shader using root parameters. So in GPath submodule, we need to change the number of root constants to include 3 constants, and in the render function, we can put the width, the height, and the frame number in an array and pass it to our shader. And there you go. We got ourselves a nice little Mandelbrot fractal. Resizing the windows, you can see that the back buffer is not properly resized yet. Going full screen, you can see the picture becomes stretched and pixelated. Also notice the color banding here. This is easily fixed in the shader by changing this formula. It came from the internet and I didn't really care enough to figure out how it works, but it does get rid of the color banding. I'm already really happy that we finally got something visually going on after all this time writing code. In the next video, I'm going to work on resizing the back buffers and also improve the way we handle resizing of windows. I hope you enjoyed this video. Thank you for joining me and I'll see you next time. Thanks for watching. If you like this video, please feel free to like and subscribe. If you join me on Patreon, you'll get access to the code on GitHub, so you don't have to type everything over from the video. Plus, there are also other nice goodies and rewards exclusive to my Patreon supporters. Please use the link in the video description to check them out. I hope to see you next time. Until then, take care and happy game engineering!